In celebration of National Space Day, we journeyed beyond textbook into the vastness of imagination and innovation. Our young explorers stepped into the shoes of scientists, and with curious minds and creative hands, they built their very own space rovers. Each model was more than just a project, it was a dream in motion, a tribute to the spirit of discovery that fuels every space mission.
As part of our project on space exploration, our team successfully designed, engineered, and built a functional rover prototype. The goal was to simulate the working of a space rover similar to those used in real planetary exploration missions, such as NASA's Curiosity and Perseverance. Our rover is capable of navigating different terrains, collecting data, and performing basic scientific experiments. This project outlines the challenges we faced, the components we used, and the process we followed. Space rovers are robotic vehicles designed for planetary exploration, capable of navigating terrain, collecting data, and performing scientific experiments. Our project took inspiration from notable rovers such as NASA's Curiosity rover, which explores Mars' surface, analyzing geology and searching for signs of life, whereas NASA's Perseverance rover investigates the G0 crater on Mars for evidence of ancient life. The Spirit and Opportunity rover pioneered surface exploration on Mars, searching for evidence of water. Functions our rover can simulate are terrain exploration, data collection, and scientific experiments.
We have used various electronic components for building the rover. For communication purpose, we have used antennas for wireless control signal reception and transceivers facilitating data transfer between rover and operator. For navigation and control, we have used GPS module, which provides positional data for outdoor testing, and onboard microcontroller, which act as a brain of the rover executing control commands. For power supply, we have used solar panels, which supplement battery power during daylight operations, and rechargeable batteries that stores power for nighttime or indoor tests, and power management system, which regulates voltage and prevents power surges. And scientific instruments used here are cameras, which is used to capture the terrain images of analysis, sensors, which measure temperature, humidity, and light intensity. Other components we have used are motors, drive wheels, and control robotic arm movements, wiring and cabling, which ensure data and power flow between components.
Scalability, mobility, and power and electronics. Design and engineering challenges faced by us. Ensuring the rover's proportion accurately represented as real rover designs while maintaining practicality for testing. Designing a wheel and suspension system allowing smooth movement over uneven terrains is mobility. Programming, communication, and sensor integration are the major technical challenges faced by us. Writing and debugging code for navigation, sensor reading, and semi-autonomous movement, calibrating sensors for accurate data collection and varying conditions, establishing a realistic link between the rover and our control system for smooth operation.
Some of the practical challenges faced are budget constraints, managing limited funds while sourcing quality components and materials, balancing design, construction, and testing phases within our project timeline, choosing lightweight yet durable materials for the rover's body and frame.
The successful development of our rover prototype has given us a practical understanding of how real space exploration vehicles are designed and operated. We overcame significant technical, design, and resource-related challenges, ultimately building a functional system capable of navigation, data collection, and environmental monitoring. This project not only deepened our knowledge of robotics and electronics, but also gave us insight into the complexities of actual space rover missions. Our work stands as a small-scale yet valuable simulation of planetary exploration technology.
Hello everyone, it's me Avantika B. Jijil and I'm here to talk about my model of Chandrayaan 3. which is a part of India's space program led by the Indian Space Research Organization. Chandrayaan 3 is the third mission in the Chandrayaan series and was launched on 14 July 2023 from Satish Dhawan Space Center in Sriharikota. It successfully landed on the moon on 23 August 2023. The rocket used for this mission was the GSLV Mk3 model, which carried a propulsion module, a lander named Vikram, and a rover called Gaganyaan. First, the spacecraft orbited the Earth and then the moon's orbit. After that, the propulsion module and the Vikram lander separated and the Vikram lander made a soft landing on the moon's surface. India named the place where Chandrayaan 3 landed as the Shiv Shakti point. After Vikram lander landed, the Gaganyaan rover rolled out and began exploring the moon's surface. It took pictures, conducted experiments, and helped scientists learn more about the moon's minerals and temperature. This was a huge success because India became the first country to land near the moon's south pole on its very first attempt. I am glad to share this model and present the story of Chandrayaan 3, which shows how hardworking and brilliant our scientists are.
The Gaganyaan mission is India's first human spaceflight mission led by ISRO, Indian Space Research Organization. So this rocket's name is GSLV Mk3, also known as Geosynchronous Satellite Launch Vehicle Mark III.